Okay, welcome back to 152. We'll get started. The recording is rolling. All right, welcome back. So we're going to continue where we left off today. There will be a two-slide quick announcement spiel in the middle of the lecture. So we'll just continue where we left off for now, and we'll get to it when we get to it. So we're going to pick up where we left off. We had started talking yesterday about memory technology, old memory technologies like core memory, relays, mercury delay lines, all sorts of mechanical gears, all sorts of things that were used up until the 1950s or 60s. And we had just gotten to IC memory and integrated circuit chips towards the end of last time. And that was on the heels of talking or introducing more complex pipelines. We had gotten through 5-stage pipelines and started talking about pipelines with multiple parallel functional units, sometimes pipelined, sometimes unpipelined. Potentially, I didn't say this explicitly, but it was on the slides, multiple register files. For example, a register file for integers and a register file for floating point operations. That was especially relevant when we talked about the two-way superscalar machine at the end of the pipelining discussion. And so now we're talking about memory. And now that we've gotten into IC memory, we're going to build up from the basics and learn a bit about the main memory technologies that we use today. We're going to use DRAM to kind of get the concepts down, and then we're going to do a quick compare and contrast between DRAM and SRAM. The spoiler alert is that if you understand the differences between a DRAM cell and an SRAM cell, how these cells are organized into larger memories from like a 30,000-foot view looks similar. So we'll learn about how they're organized in terms of DRAM, starting at the cell level all the way up, and then we'll kind of move horizontally and talk a little bit about SRAM differences and similarities. Then we'll start talking about how these memory technologies influenced the design of computer memory hierarchies. We'll start talking about caches and go over the ABCs of cache design, which may at some level have been covered in 61C, so some of this may be review, but some of it may be new. All right, so today we're going to start with DRAM and DRAM cells. So here we have on this slide a DRAM cell. DRAM was invented in the 70s by Dennard at IBM. It was designed to be an extremely dense memory, where when we say a memory is dense, we're referring to how many components are needed to store a bit. So recall from last time we spoke briefly about core memory and how each bit of core memory was stored in one of these toroid magnets that were hand-strung with perpendicular wires. These hand-strung toroid magnets were not very small and not very dense. This toroid magnet component was quite large. And so what we're going to try to do is kind of scale our memory down and see how few components that can be scaled along with process technology and automatically fabricated, how low can we get, so to speak, to design as dense a memory as possible. So what Dennard came up with was this for the DRAM cell. The way to kind of view this picture, I'm going to use, if I can figure out how to do this again. Okay, the annotate button. Let me see if I can. Oh, right, it's on the side like this. So let me try scribbling. Okay, good. I can scribble, and then we can hit undo. Okay, so what I'm going to do is similar to last time we did this. I'm going to kind of spin this around so that I can see what I'm doing. So the way to kind of view this cell, forget about how multiple cells are dealt with. Let's just live in a world where we want to store a single bit in this entire DRAM. The way to look at this cell is the horizontal wire is like the address. It's a 1-bit memory, so we just have one address bit. And the vertical wire labeled bit or bit line is like your output bus, your data out. And the thing in the middle, the NMOS or access transistor and the capacitor that on the other side is going down to the reference voltage or ground, is how we actually store the charge. Who here in some class has seen an NMOS or a PMOS transistor, this symbol here? Okay, almost everybody. So people know that this is a switch. And so the idea behind this memory, the way to kind of think about it, is that the transistor is a way of isolating the charge on the capacitor, oop, where did my mouse go? Which is to the left of the access transistor. And the capacitor itself you can think of as like a battery, which stores charge, with the last charge, whether you want to store a 1 or a 0 bit in the cell. You can kind of think about it as a bucket. If you've taken EE40, or I believe EE40 was replaced with something else, but like passive units, you can think of a capacitor as a bucket that slowly leaks out its charge once it's filled. If you apply a potential to it, it charges up, and then once you relax that potential, it slowly discharges. So we kind of have a leaky bucket of charge here. So the way it works is when you want to, let's suppose that there's charge stored on this capacitor. So we're currently storing, let's say, a logic 1 relative to the reference voltage. So we're currently storing a logic 1. Let's suppose that we want to get this bit out. What we're going to do is we're going to apply a 1 to the address. So we're going to bring to voltage VDD, the high voltage, the address or the word line. And what that's going to do is turn the access transistor, because this is an NMOS where the circuit is closed if you apply 1 to the gate, that turns this into a wire, and it allows the charge that is stored and slowly discharging on this capacitor to dump out onto the bit line. So if you like, you can think of this as like a leaky bucket where the water level is slowly going down, and if we close the access transistor to connect the bucket to the bit line, we're dumping out the charge onto the bit line. And that's going to be what drives the quote-unquote data out signal so that we can get our bit out. Now, because this is a bucket, when we connect it to the bit line, we're dumping the charge out, and therefore the read operation that we're doing on this DRAM cell is destructive. So whenever we connect the capacitor to the bit line, taking the water in the bucket, dumping it out on the bit line, we're going to have to explicitly, if we want to read the value there sometime later, which we typically like to do in memories, we're going to have to explicitly, after the read, perform a write back of the original value. The write operation is kind of the reverse. What you do is you apply, I'll not get rid of my annotation just because everything is going to get reused. You're going to apply a 1 to the same word line, closing the circuit. You're going to apply charge to the bit line. You're going to apply a potential of VDD if you want to store a 1, VREF if you want to store a 0, and that's going to drive the bit line and reset the capacitor. It's kind of like applying a potential to a capacitor and charging the capacitor up. In other words, kind of flushing the bit line with water and refilling the bucket that you just dumped out. Okie dokie, I'm going to get rid of this. Clear all drawings. Okay, there's one more step. I said this was a bucket, but if you remember capacitors from EE40, capacitors leak over time. So this is a leaky bucket. So even if you don't access this value, even if you don't apply a 1 to the word line, the charge on the capacitor is slowly going to drain, and eventually whatever value you have stored on that capacitor is going to disappear. So in addition to this being destructive read, where whenever you read out, you have to write back if you want to read the value again, you're going to have to asynchronously, and in addition to that, perform some asynchronous, what they call refresh operation, which refreshes the value that's stored at the cell. So basically what a refresh is just a read that occurs to any DRAM cell whose contents you want preserved at a particular interval. So imagine I want to read this cell. I can read it just the way that we described, but sometime in the background later, when I'm not reading it, a circuit which accesses the DRAM is going to perform what is tantamount to a read as well. And that read is going to first dump out all the charge in the bucket onto the bit lines, read the value out, write the value back, and when the value gets written back, the amount of water in the bucket will be restored to its full level. So there's kind of two overhead operations here. There's the fact that this is destructive read, and there's this refresh operation. And that's kind of the way to think about DRAM. It's very dense at the expense of speed. We've gotten the ability to store a single bit down to a single capacitor and an NMOS. But what we're paying for that are these overhead operations that are not associated with the operation that we actually want to perform. Any questions on a DRAM cell? Okie dokie. To the left of, or right of the slide, pardon me, is what a DRAM cell actually looks like in real life. So this is actually pretty cool. We have the access transistor here, so like recognize the shape of like a transistor here. We have the word line, which is right above the access transistor. Here's the channel of the access transistor. And this whole structure here is the logic that's needed, these circuit elements that are needed to store this bit. So remember back from, again, I don't know what this course is called anymore, but whatever course where they introduce what a capacitor is like two electrodes, like two plates with like a dielectric in between. And the potential is across this dielectric between the two plates. So what we have here is the first electrode, this thing in blue. It's kind of like snaking its way around. The orange is the dielectric material, kind of in between the electrodes. And then at the very top, the purple, we have the other electrode. And if you want to see what this looks like at an even more kind of physical level of detail, we have a picture of it right here. And you can see it kind of looks like we've drawn. So like what we have in the middle of the slide is like this sucker here. And then we have another DRAM cell here. So this is what a DRAM cell looks like. Okay, let me turn annotation off. All right. Uh-oh. Let me kill this first. Clear all drawings and close. Okay, great. So here's a DRAM cell. This is what DRAM cells look like nowadays. So old school DRAM cells are kind of like these bulky shapes. And again, the design philosophy with DRAM was let's go as dense as possible. We want the access to be fast, but we're going to prioritize density over access speed. So it started looking like this picture on the right, but this was still not dense enough. This shape is kind of bulky. It's difficult to cram more of these structures in for unit area. And so modern DRAM cells look a little bit different. So the first picture in the back is just like an array of DRAM cells. I'm jumping a little bit ahead because I haven't spoken like about what multiple DRAM cells look like, but imagine that these are two cells that are next to each other in an array, and the analogous picture is just this kind of slightly differently oriented array. And what's kind of interesting here is the shapes of the capacitors look a little bit different. So the ones on the previous slide were kind of these like stubby things. On this slide, what the DRAM, in particular the capacitors look like, these long tubes are the capacitors. They look much kind of more elongated and like stripped down. And this is what DRAM cells look like today. So this technology is called deep trench capacitors, and they go by kind of like various names, but that's like one of them that you may recognize. Does anybody have an idea why you'd want these like super deep, long, thin capacitors as opposed to kind of the squarish ones from the previous slide? Does anybody have a guess? Yeah. Can you speak up a little bit? That's exactly right. That's exactly right. So silicon is, or the way that we design chips, can take advantage of 3 dimensions. So on the one hand, if you think about the die area as a two-dimensional surface, maybe all you have to work with are these kind of like cuboid capacitor structures. But with capacitors, as mentioned, the surface area of the plates is what's important. So instead of having these kind of like cuboid shapes, if you can utilize the third dimension, you can kind of like stretch the plates out and thin them out and pack more in a given two-dimensional surface area if you view the chip top down. And so that's the reason for building them like this. This turns out to be really hard to build. So this kind of material in between the long, thin capacitors, I'm not sure if it is coming out on the slide, but it says mesh SiN3, that's silicon nitrate. They call this kind of like the mesh array that the capacitors are built in, and it's actually very difficult to kind of build these tubes straight down such that they don't touch one another or that they're not slightly angled so that like eventually they get too close to one another. It's actually very difficult to do that. And that's kind of the challenge of this design, kind of placing these tubes in a way that they don't touch or get too close. If they get too close to one another, or God forbid they touch, you'd either have a short, or due to inductive effects, you'd have charge sharing across capacitor cells, which is obviously not something that we want. Well, that's what DRAM cells look like today. So here we're going to zoom out one level. We're going to go from a DRAM cell to a DRAM, what is called subarray. So the way to kind of view this picture, I'm going to go back into annotation mode, if I can find my mouse. Oh, I need to turn on annotation mode, and then we'll do this all over again. Squiggle. Okay, cool. Okay. So what we were looking at before is like this part of the diagram. So the red lines are the word lines. The green lines are the bit lines, and the little squares, oh, I'm actually offset a little bit. I guess the slide is reversed, so it's like this, because we have one of these squares attached to its left neighbor bit line and its upper neighbor word line. Okay. So what we were looking at before is like this cell here. And all we've done is we've added a bunch of word lines in the horizontal or vertical dimension with the word lines running horizontally, and more bit lines in the left-right dimension where the bit lines are vertical. So you can think of this similarly to how you think about memories if you've taken any other like digital design RTL class, where you have rows, which are like your words, and you may not think about columns, but you understand what data output is. So you can kind of think of each one of these word lines now as accessing one word in the DRAM, and the bit lines just carry the signal to the output. So the way that this works is, what we're going to do is we now have more than one address line, or more than one address bit. And in particular, we have multiple bits for the address, and they serve one of two purposes. Either the bits are going to be used to pick a word line, or the bits are going to be used to pick a subset of the columns once a particular word line of cells has been activated to subselect which bits we actually want. So you can kind of think about it like this. We take our address bits and we split them off. Some of them go, so log of the number of word lines that we have go to this structure called the row address decoder, or I guess log of n, pardon me. Go to the structure called the row address decoder. And what that decoder is going to do is it's going to take my n address bits and blast it into a one-hot signal where one of the word lines is activated and the rest are set to 0. So activated equals 1, not activated equals 0. So let's just suppose, for argument's sake, that this decoder, this binary to one-hot converter, decides to drive this word line. So what that's going to do is it's going to activate the access transistors, closing the circuits for all of the cells in that given row. And whatever the cell values are in these squares here are going to get dumped out onto the bit lines. And just for reference, the number of cells in a word line is usually like in the multiple kilobytes. It's like 16 kilobytes is a pretty reasonable row size. So a lot of bits get dumped onto the bit lines when we do this. So with that all said, who has an idea for what we're going to be using the rest of the address bits, the ones that are going to be going into the column decoder and sense amplifiers? What do you think we're going to do with them? Any volunteers? Yeah. Exactly. It's basically a big multiplexer. The electrical details are a little bit different, but when you see column decoder and sense amps, you can kind of think of that as a mux. So what we're going to do is we get all of the words at this row out, and then we're going to down select with the remaining M address bits, a subset of them that we actually want. So something, yeah, question. Say that. It's just the address bits. So you have some number of address bits, n plus m. So imagine just an address that your program can understand. And what's interesting about DRAM and any memory technology is once you hand your address to the DRAM, it can decide how to use different subsets of those address bits in one of a number of ways. What it is deciding to do here is take the n plus m address bits, and it doesn't say this, but let's just imagine for argument's sake that the upper bits are the n bits and the lower bits are the m bits. And I apologize for these letters being so close to one another in terms of what they sound like. We're going to take those n bits, and that's going to down select which row we want. We're going to take the m bits, that's going to down select which column we want. But the DRAM controller, it's the circuit that kind of controls access to the DRAM, which we'll talk about in a few slides, is responsible for these decisions. But you can think of it as just an address. Yep. The sum of two numbers. You can think of it as just, this is a bus that is n plus m wide. That's all that it means. Yep. Good question. Good question, because we're going to get to how many wires are typically used to access a DRAM controller in a slide, or a DRAM in a slide, and it's not n plus m spatially, it's n plus m temporally, but we'll get to that in a second. Okay, so this is how you get bits out of a DRAM. And remember, when this operation happens, you activate the word line. That's going to charge the bit, all the bit lines in the array. All the values come out. You're going to write back all the values again because reads are destructive. Then the value that you originally read out is going to be passed through the column decoder. And then if you're not accessing the DRAM at some time later, there will be this so-called refresh operation, which comes around and makes sure to touch all of the cells to bring their charge up to the nominal maximum charge. And this refresh, now that we're looking at this array, this refresh operation is an operation that you can think of as being scheduled to be along all of the word lines over time in the DRAM. So you have this array here, and perhaps the first refresh happens to the first row, maybe 7 microseconds later, another refresh will happen, and it will arrive at the second row, and then the third row, and then the fourth row, and then just kind of like wrap around like that. And the refresh is scheduled such that the time in between any two refreshes to the same row cannot exceed what the manufacturer has figured out is like the charge decay time for the capacitors in the array. Oops. Any questions on DRAM arrays? All right, let's continue on. Oops, and naturally I've got to get rid of this gunk, annotate. Get rid of, clear all drawings. Beautiful. Okay. Zooming out even further. So we've looked at a DRAM cell. We've looked at a DRAM array. A DRAM DIMM, which is the whole DRAM memory, is several levels above that. So everybody's probably gone to Fry's and had to replace DRAM DIMMs in like their laptop and desktop systems. So this is how DRAM is usually connected to consumer devices. So the DIMM is made up of a bunch of these chips. So if you look closely, again, the slide contrast is not great, but on the DIMM, there's a bunch of chips. These chips within them are a bunch of the DRAM subarrays that we saw earlier. If you flip the chips over, there's usually chips on the other side. So there's as many chips as they can cram on this thing. Each one of the chips is made up of several what are called logical banks. And each bank is made up of a bunch of the subarrays that we just saw. And in each of the subarrays, there's a bunch of cells. What's the difference between a subarray and a bank? Basically, a subarray is a bank, is a collection of subarrays that can be logically accessed at a given time. So it turns out that a lot of the time that it takes to access the DRAM is not just passing the address from your laptop or desktop to kind of the pins at the edge of the DRAM. It's actually going into the DRAM, going into the different chips, going into the subarrays and the cells, and dragging your bits out. And so what the DRAM manufacturers invented was this like logical collection of subarrays called a bank, which can each be accessed at a single time, but such that different banks can be accessed concurrently. So when you have multiple requests going out to DRAM, it's not that you send a request out and you have to wait until your data comes back to send the next request. You'll send a request out, and as soon as your request has cleared the wires that connect your laptop CPU to the actual DRAM pins, you'll be able to send another request out, as long as your second request goes to a different bank of subarrays on the DRAM chip. So in the background, the first bank is kind of working on your request, and it's going to return your data sometime later. If you stagger and shortly after that send a request to a different bank, it's going to be able to, in a pipeline fashion, start processing your second request. And then you'll get your first response out, and then in short order, you'll get your second response out. So there's actually kind of a similar type of pipeline parallelism that you can do when you consider the entire DRAM organization that we have in normal pipelines that we've studied so far. Yeah. Yeah, sure. Yeah, so typically the way that this varies depending on actually how you've set up your machine. Some of this control you have in your BIOS, but there's kind of two ways that a write can happen. The first way is there's a structure underneath the column decoders that we haven't talked about called the row buffer, which buffers the previous row that you've read or written from the DRAM. You can think of it as like a one-word cache. And so one way to do the write is if the data that you already have is already contained in the row buffer, you just merge the write into the row buffer and you're done. On the other hand, if you either don't have the row that you need in the row buffer, or, and this is the part that you can actually configure in your BIOS, you can go into your BIOS and under like the DRAM section, it says open page, closed page policy. The word page has nothing to do with virtual memory because, of course, these different communities didn't talk to one another and therefore call completely different concepts the exact same thing. So there's a way to actually turn your row buffer off. So if you've turned your row buffer off, or if, again, the row buffer is on, but the data that you want is not in the row buffer, what you're going to have to do is read the data out and then merge the write that you want in and then write it back. Yeah. This is a common degree of inflexibility that both DRAM and SRAM have. When you activate a word line, you're going to get all the bits out for that word, which may be more bits than you actually want, or for that matter, you actually own, if you want to look at it from a security perspective. And if you're writing, you don't have a way of selectively writing back. You have to read and then write. So yeah, this is a good question. Okay, so this is the whole picture of DRAM. One other kind of note here, going back to the previous question on N plus M address lines. So again, going back to the DRAM philosophy of maximize density potentially at the cost of access latency. So we're willing, if we're able to make things more dense, we're willing to slow the DRAM access time down. What they will also do is instead of just having a wide address bus where your entire address, let's call it the n plus m bits, are in n plus m wires, instead of just having all the wires there at one time that you can just pass your address to, which is kind of the way that you think about accessing like a RAM. The way that it's organized in DRAM is that it's temporally multiplexed and serialized over fewer wires. So I think that this is DDR2. It may have changed in more recent generations. DDR is like DRAM, it's like DRAM standards that have evolved over time. The number of address lines that you have are only 12, or the number of address wires that you only that you have are only 12. You put 12 bits of address in one cycle and send that to the DRAM, and then you're going to put more bits of address on those 12 bits later. And so you're kind of serializing the address out. And what that allows the DRAM to do is have less pins, which is better from an area perspective, which helps with the whole density argument. So really, they're kind of like dialing all dimensions up for density at the cost of access latency, because of course, having all of the address bits there at time one, you could potentially get your data out sooner. Yeah. That is a good question. So there's actually three actors here. There's the CPU, there's the DRAM controller, and there's the DRAM DIMMs themselves. The DRAM DIMMs, interestingly, are mostly passive devices. There's not internal logic inside the DRAM DIMMs, which is kind of like orchestrating things. The process of doing the access is driven by the DRAM controller, which is a custom circuit, usually these days at the edge of your processor die. But in the old days, it was off chip on this separate PCB called the Northbridge. And that's what's kind of orchestrating accesses to the DRAM. And your CPU just knows about cache hits and misses, and it talks to the DRAM controller through that interface. Once you send the signals over to the DRAM from the DRAM controller that say, open a bank, grab data, despite the DRAM being a passive device, it will do a thing sometime later. That thing might be the data will appear. So once the DRAM controller initiates an access, even though it's a passive device, as long as you keep it connected to the power and you send those commands, just the way it's designed, you're going to get your data out sometime later. And we'll see actually a timing diagram of how that works in a few slides. Yeah. Yeah, the DRAM controller does the write back itself. We'll actually see like exactly where it does the write back. And there's some flexibility on when it's done to kind of like hide the latency of that operation. Yep. Other questions? These are all good questions. Okay. Here's another way of organizing DRAM. So when you're running programs on an Apple M1 and you benchmark your DRAM access latency, you might be surprised as to how fast it is. That is because on the Apple M series CPUs, they put their DRAM chips on the same package as the SoC. So you really can't see this, given these slides' contrast. But there are two of the DRAM chips that previously were jammed onto that DIMM on this black rectangle, or black square, which is the package for the M1 chip. So accessing DRAM on Apple M series devices is especially fast. You don't have to go through some of the stuff going off your actual package onto, going back to this picture, through the pins of the DRAM, which are these kind of golden pads here, to get to the actual DRAM chips. It's actually closer to the SoC. Okay, now to Ronit's question, when does the write back happen? We have this very wordy slide to kind of walk us through all the operations. The high order bit here is that the way that DRAM is designed, again, we have rows and we have columns. You might imagine, if you think of a memory with just a flat address input, a data in, a write enable, a data out, that when you put your address in, it's just like atomic, you get your data out and you're done. But in DRAM, they've cleverly designed the array so that you can actually kind of stagger how you look it up. You're not simultaneously driving the word line and driving the column decoder to get the actual bits of interest out. You're doing this kind of in a staggered fashion. And the reason that they like having it orchestrated so it works in a staggered fashion is so that they can split the addresses up and thin out the number of address pins on the DRAM. So there's kind of 2 steps, 3 steps, but let's focus on the first 2 for a second, to accessing a bit in DRAM and getting it out. And that is the what is called row address strobe, the RAS operation, and then the column address strobe. Has anybody designed, I think it would be for 151, a DRAM controller on an FPGA? Is that something that y'all still do these days, designing a DRAM controller? So no one's seen a data sheet that has a diagram that looks like this? But you haven't parsed it. Okay. So back in the old days, in 151, we had to design DRAM controllers, remember, CPU, DRAM controller, DRAM DIMM, that orchestrated touching and activating, sending different commands to the DRAM at a very specific time. That is what we're going to see on the next slide. Conceptually, what we're going to do is a 2-step process. We're going to do this thing called the row address strobe. All that means, the word strobe is kind of scary, but it doesn't really mean anything. All it means is we're going to send the subset of bits in our address that are going to be responsible for choosing a row over the address lines, and that's going to kick off the process of opening a row of cells and getting the data dumped onto the bit line. So that's kind of like the first step of this operation. The second step, and to answer Ronit's questions, I'm not going to read all of the words on the slide. Feel free to look it up and kind of like talk through conceptually what's happening here. But just because Ronit asked, where's my mouse? Sense amplifiers drive bit lines full rail to recharge storage cells. That's where the write back happens. So at the end of the row address strobe, we open a row of cells, we dump all of those cells onto the bit lines, and kind of seamlessly in the background, that's where we're going to slip the write back operation in. Again, we're going to try to kind of like overlap this operation with the other stuff that we have to do. Second thing that we have to do, in a separate cycle, it's actually not necessarily one cycle, it's some amount of time later, we're going to put the rest of the bits which are responsible for picking which columns we're interested in on the address lines, and that is going to be what pulls out the subset of columns and pushes them to the chip pins. Can anybody tell me why we do RAS followed by CAS as opposed to CAS followed by RAS? Why does this order make sense? Anyone? Yeah.
Because after RAS, it takes some time for the bit lines to be driven to the rails. So you may as well get that started while you start living.
That's exactly right. So going back to our picture, there's no sense in sending the column address first, because the column address is like a select signal into a multiplexer. There's no reason to send that select signal to the multiplexer before we have the inputs to the multiplexer ready. The inputs are like all of the bit lines coming down. On the other hand, if we do RAS followed by CAS, then what that's like saying is, okay, first I'm going to activate a word line. I'm going to get all of the cells at that row dumped onto the bit lines. That means that RAS kind of kicks off the process of getting all of the inputs to the MUX, the column decoders, ready, so that when I finally send the MUX select signal, which is the CAS operation, the inputs are ready, I can get my outputs out. Very good. Okay. So we have row address strobe, we have column address strobe. Finally, we have this thing called precharge. So this is just yet another thing that is kind of baked into DRAM's design, which favors density over speed. So we won't see how you can do better than this until we briefly talk about SRAM cells. So I'll just explain what this is for now, and then we'll describe briefly how an SRAM does not need to do this operation, even though SRAMs do this operation for optimization purposes, but it's actually fundamental in the case of DRAM. But we'll just explain what it is now. So we have to do this thing called precharge. What precharge means is we have to take the bit lines and we have to set them to a known voltage, a reference voltage. You can think of the reason for that being that when you dump charge out after activating a word line onto the bit lines, not all of the charge gets sucked out by the sense amplifiers. There's like some residual amount of charge left over on the bit lines. And this kind of goes back to the principle of DRAM. It's designed to be extremely dense. These capacitors are actually relatively weak. So the amount of potential difference that happens when you open the access transistors and dump the charge out is extremely slight. So there's like very slight variations of potential difference on the bit lines, and it doesn't get all like sucked out at the end of the operation. And so what pre-charge does is clean it out so that when you open the next row, any residual charge there on the bit lines does not interfere with the values on the capacitors to the newly opened row. So it's kind of like a way of kind of resetting the system so that if you want to use the bucket analogy, when you dump the bucket out, you want to make sure that you dump it out onto like dry ground. You don't want it to be like damp ground, which could interfere with the amount of water that you dump out. Usually you pre-charge to VDD over 2. Does anybody have an idea for why that's a good idea? Pre-charging to VDD over 2 over 0, like the reference voltage, or VDD, the high voltage? Yeah. That's right. That's exactly right. So if you set it to say vref, or let's call that 0, and you actually want to dump out a bucket which is storing a 1, you're going to have to dump out more water to bring it from a 0 to a 1 than half to 1. And so half is kind of a midpoint where if you set all the bit lines to that, the potential difference needed to register as a logic 1 or a logic 0 is minimized if you have no assumptions on like the data patterns written there. Okay, each of these steps has a latency associated with it. Again, this is like a passive device. So when I send a row address strobe, I will send sometime later a column address strobe. After I send the column address strobe, sometime later, this will all percolate through the DRAM banks to subarrays to cells, and data will come out sometime later. So you can think of this as like some giant combinational circuit, which I initially send some inputs to, and the logic kind of flows through, and eventually I get my result out. And what this diagram shows is like what the DRAM manufacturers give to DRAM controller designers so that they know exactly how and when to initiate these different commands. So I will leave CS151 or a similar class for you to become intimately familiar with a datasheet like this. But suffice to say, you can see some of the operations that we've discussed so far. So here we have, these are signals that correspond to pins on the DRAM DIMM that we saw earlier. So these are these are like wires that are associated with pins. Some of them are driven by us, the DRAM controller. Some of them are bidirectional. They can either be driven by us or they can be driven by the DRAM itself. In particular, these are driven by us. So this is the clock. So the DRAM is a clocked circuit. The command driven by us, address bits, and bank addresses. So we control bank address bits, we control address bits. Really, you can think of the bits that are used to determine the bank as just a part of the address, but the DRAM DIMM designers are nice enough to expose which bits are responsible for choosing banks versus which bits are responsible for choosing everything else about the address. Does anybody have an idea so this is like the ISA of the DRAM. Why would they actually expose at the level of the ISA the bank bits as opposed to any other address bits? Any ideas? This was a big decision on their part, so they must have had a good reason to do it. You take the counterfactual and instead live in a world where the bank address bits are not explicitly split out of the address. So all you're presented with as the user is like an opaque address bus and you have no idea which bits are responsible for the RAS versus the CAS versus the bank. Yeah.
Back and so if we are able to distribute our data from deeper backs, then our ratings will be faster.
That's exactly right. The primary way that we can achieve pipeline parallelism in a DRAM is by arranging accesses so that different banks are looked up concurrently. How your data is mapped otherwise is less important. And so the DRAM manufacturers recognized this and said, here's a bunch of address bits that you can drive, and we're not going to tell you anything about their semantics because it doesn't really matter. However you decide to use these address bits is up to you. On the other hand, we're going to expose these bank addresses because if you understand what the bank addresses are for, then you as the DRAM controller can actually schedule accesses to maximize concurrency. And modern DRAM controllers do exactly this. They will queue up addresses and select which addresses to send to the DRAM in which order to maximize bank level parallelism. Yep, that's exactly right. Great. Okay, so going back to this picture. What this data sheet is saying is you as the DRAM controller, if you want to send a row address strobe, you set values to these wires in a given clock cycle. Several clock cycles later, where the clock is a clock that you drive at 200 megahertz per the DRAM standard, you send the column address strobe, which is just you place different address bits on the column wires, and then you pre-charge. And going back to what we said earlier, after you do the column address strobe, sometime later, data comes out of this line called DQ, and this is your output data. DQ is this bidirectional set of wires which either contains data that you're driving in the event of a write or data that you're reading from the DRAM in the case of a read. So you can do either a read or a write at any given time. Again, in the spirit of high density memory, we're sharing wires between read data out, and write data in. Okay. All right, that's it with DRAM. Well, that's almost it with DRAM. We're now going to, now that we've kind of seen the whole picture of DRAM, we're going to briefly contrast it with SRAM. Who here has seen an SRAM cell before? Okay, most people have seen an SRAM cell. So in that case, I'll kind of breeze through this. Here's a DRAM cell. We have a word line, we have a bit line, we have an access transistor, which is an NMOS, we have a capacitor. We've talked about how this, when you kind of organize it into larger hierarchies and choose how you're going to do write back and refresh and pre-charge, really enables high density, maybe at the cost of access latency. SRAM is the exact opposite. So this is a 6T SRAM cell. 6T because it's made up of 6 transistors. Each of these inverters, if we're in CMOS technology, is 2 transistors, an NMOS and a PMOS, plus 2 access transistors. And a bird's eye view, this looks pretty similar to a DRAM cell. We have a bit line. We have 2 bit lines here. We have a bit line and its complement. But hey, they're all still bit lines. We have a single word line, that's the same as DRAM. And instead of 1 access transistor, we have 2 for the 2 bit lines. And the way that we're storing charge is not with a capacitor, but with these cross-coupled inverters instead. Okay, so why does SRAM look like this? So SRAM is the opposite of DRAM. Instead of prioing density and then trying to get whatever low access latency you can get after you've maximized density, SRAM is about minimizing access latency, potentially at the cost of density. So this cell, who knows what we get from the cross-coupled inverters relative to DRAM? Who can wager a guess? What's the benefit of those cross-coupled inverters? Anybody? So what DRAM operation do we no longer need for SRAM? Refresh, that's exactly right. We have these cross-coupled inverters, which means that if you store a 0 here, you're going to get a 1 here, which is going to propagate a 0 here, which is going to reinforce a 1 here. Much like, mercury delay line memories, just a lot more modern. What this does is self-reinforce the bit that is stored there, which means that instead of thinking about an SRAM cell like a leaky bucket, you can think of it as like a faucet that is perpetually dumping charge into the system to restore whatever bit value is there. So no refresh, no more refresh. Furthermore, because of this self-restoring system, reads are not destructive. So in an SRAM, if you read a value, you need not write it back to restore it because you're not like dumping charge out from a bucket onto the bit lines. You're just kind of turning on the faucet and connecting the faucet to the bit lines. And once you disconnect it by turning off the access transistors, that's perfectly fine. The faucet still keeps on flowing. Don't need destructive reads. So no destructive reads, no refresh. Bit lines. Why do we have bit line and bit line prime? What does this enable us to avoid in SRAM, at least fundamentally? Precharge. So by having bit line and bit line complement, we're either going to push onto the bit lines a 0 and a 1 or a 1 and a 0. The sense amps are going to sense the difference between these two. And whenever we activate the word line again, we're going to apply fresh charge, again in either the 0 or 1 configuration if we're storing a 0 logically, or a 1 followed by a 0 if we're storing a 1 logically. And we no longer need to pre-charge the bit lines. As it turns out, modern SRAMs actually do, however, precharge the bit lines. They precharge the bit lines to the same, usually VDD over 2 neutral value that we precharged the DRAM bit lines to, but not because it's fundamental. They do it to decrease their read time. If you precharge to VDD over 2, you can more quickly adjust the bit lines on the next read to whatever value you need. And so your access latency for the next read is reduced, but it's not needed fundamentally. Okay, so just to kind of recap, DRAM cell versus SRAM cell, along what dimensions, yeah. Oh, you were just stretching, okay, cool, yeah, no problem. Along what dimensions are these different? So DRAM optimized for density and then speed, SRAM optimized for speed and then density. You can kind of see that play out here. 1 access transistor, 1 capacitor, 6 transistors, and some SRAM cells are more than 6 transistors, like all the way up to 10 or 12 transistors. Time multiplexed address pins for DRAM. With SRAM, you usually just apply all the address pins in one shot because you can afford to do that, so you can get your data out sooner. Reads are not destructive for SRAM, static, no refresh, whereas in DRAM, reads are destructive and you have to refresh every few milliseconds. Okay, so this gives you kind of a sense for these two different memory technologies. Now, what does that mean for CPU design? So as it turns out, so kind of going back, we're going to kind of roll back a little bit and start talking about pipelines again. So we now know what the memory block looks like. We've been studying what the CPU block looks like. What does it mean when it comes time to connect these together? So let's start by living in a world where all we have is DRAM. So we have our CPU and we have our DRAM, and we're going to just ignore SRAM for a slide or two, and then we'll come back to SRAM. So it turns out, perhaps not surprisingly, that if all you have is DRAM, you're completely and hopelessly dominated by your memory access time. So going back to the metrics that we defined a lecture or two ago, we have latency, bandwidth, and occupancy. The latency of a memory access is to DRAM, is orders of magnitude greater, guaranteed, than the processor cycle time. So going back to our 5-stage pipeline, you'd immediately, going back to CPI and looking at bandwidth, have a CPI not of 1, but of 1 plus whatever this very large memory access latency is. So in this kind of simplistic design, we're completely bottlenecked by memory. Not to mention, even if you are smart with exploiting bank level parallelism, we don't even have the CPU smarts to exploit it right now, because our CPUs, with the exception of the CDC 6600, are just single in order, and there's no way to schedule memory accesses in a clever order to exploit banks. So we're kind of as bad as it can get based on our current understanding of how pipelines work. And not only that, this has been getting worse over time. So this is a graph that shows the latency gap, or the performance gap, quote unquote, between CPUs and DRAM technology from like, I guess, 1980 to year 2000. So this was like covering the golden age of microarchitecture going back to the first lecture. And you can see that CPUs were accelerating in terms of their performance at a rate of like 52% to 60% per year, whereas DRAM is scaling in terms of access latency much slower. And so not only do we have a very large gap just based on what we saw that it takes to pull data out of a DRAM cell, but this gap is getting wider and wider. And just to give kind of like some perspective here, if you're issuing 4 instructions per cycle at 3 gigahertz, accessing DRAM, which is like an 100 nanosecond latency, if you go back to the datasheet page, is tantamount to like 1,000 plus instructions that you could have fetched in the CPU. So for every 1,200 instructions that you fetch, you can perform 1 memory access. And oh, by the way, in our 5-stage pipeline, every instruction needs a memory access. So there's clearly a huge mismatch here. So just some kind of laws of nature related to this that motivate how we design memory hierarchies. The first is that the larger the memory, the slower it is to access. And that kind of tells you why DRAM is so slow. DRAM, all about optimizing and maximizing density at maybe the cost of access latency. It doesn't help you to be dense if you're small. So people typically design DRAMs to store lots of bits, meaning that they're larger. The speed of light is constant, so the time it takes to get bits out of this very large DRAM array is commensurately slower. Signals have to travel farther, they have to potentially fan out to more locations, so on. Furthermore, and this is not a law of nature necessarily, but it tends to be the case, going back to what we said made SRAM fast relative to DRAM. The access latency the access latency of your cell is also proportional to the size of your cell. So size of like the aggregate memory impacts latency. The size of an individual cell also accesses is inversely proportional to latency. So what you see on this slide is these are actual layouts of memory cells. Starting, the way to kind of read this, it's kind of flipped. So you have like A, B, C, D, E at the top, and then what A, B, C, and D, and E correspond to down at the bottom, and then like a table of what they actually, like the technical details of them at the very bottom. So the first 3 are SRAMs, or SRAM cells, and then the bottom 2 are DRAMs. And the thing to kind of take away here is that the DRAM cell is significantly smaller than the SRAM cell. This should not be a surprise, given the kind of compare and contrast that we had with SRAM a few slides ago. But just suffice to say that access latency is proportional in not the direction that we want with cell size. And so you put these two together, and this is what kind of motivates the way that we design memories today. So we have a big, high capacity, highly dense memory, which is slow to access as kind of our main memory. This is DRAM. And then closer to the CPU, we have a pyramid of smaller memories. Only one step in the pyramid is shown here, where each step in the pyramid is successively smaller and featuring less aggregate capacity and potentially lower density cells, which contribute to lower access latencies. So for levels in this pyramid that are closer to the CPU, they're faster to access. This is like registers and potentially small SRAM, but the capacity is smaller, commensurately. And as we go out, we get to larger but higher density memories if we in fact think that we need those higher density memories. Closer to the chip, it's usually register file and SRAM. This is like D flip-flops or just the SRAM cells that we saw earlier, and then farther out, we get closer to DRAM. Okay. A little administrivia, just to kind of break up the lecture for a minute. CS152, homework and labs are due tomorrow and Friday. Who here has started the lab? Who here has finished the lab? Okay. Hopefully that's not going to be problematic. CS252. I mentioned this at the paper reading discussion section yesterday at 4 p.m., but just to reiterate, project pre-proposals, we'll be going over them next week on Wednesday during the discussion section. That's next Wednesday at 4 p.m. They're due at the same time as things are usually due the night before. Pre-proposals are a bit fungible. The purpose is to get your ideas on paper or preliminary ideas, and we'll refine them and potentially iterate on them as we go. We'll put out an ed post that will start the process of crowdsourcing ideas to kind of help get the creative juices flowing over the course of today. But just a heads up, that's kind of the next week. And on the website right now, it says that there's a paper reading assignment that will be postponed a week. We've decided to get pre-proposals done now. This kind of like smoothens out things over the next month. All right, back to memory hierarchy. Any questions administratively before we go on? Yeah. Second. We are not. We so far have found that the ones that we started with are sufficient. Okay. But if anyone is experiencing something different, please let me know. Yeah. Any other questions? Okay. Okay, so just to kind of recap. Closer to the CPU, we have these small, fast memories, for example, registers. Usually the addresses are baked into the instruction. We want absolutely optimal use of these memories, so we like to be able to go to a particular location without worrying about the memory doing background evictions or anything like caches. This is sometimes called explicit data orchestration. So you're sending a physical address which looks up a value, and you're going to read or write the contents at that particular address. And the larger, slower memories are implemented using hardware caches and eventually DRAM, and usually these are at least partially managed by the hardware. The interface to these memories is not an address which looks up a physical location, but is rather the address corresponding to an address which is meaningful in your program. In other words, these memories are content addressable. They're content addressable, and hardware manages when to fill and spill and evict lines from these lower memories so that you, the programmer, don't have to think about it. And it does that potentially behind your back and potentially without you knowing, because speed is less of a premium for these larger memories. So it's kind of a trade-off in access latency and programmer complexity. Okay, so we've built up this memory hierarchy at a high level. What do memory access patterns actually look like in programs today? So this sheet shows over time on the horizontal axis and the memory address on the vertical axis what a program's memory address pattern might actually look like. And you kind of see two salient features in this picture. You might see these like horizontal blip, 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 blip strips, which indicate that a given address is accessed multiple times over time in short succession. Or you see these kind of like rectangular blocks, which look kind of like barcodes to some degree. What this in a cartoon form represents is one of several types of common accesses. So the first is instruction fetches. Does anybody have an idea of what the instruction fetch access pattern in that kind of diagram might look like? Anyone care to conjecture a guess? Yeah. Like a horizontal line? And that would be indicating what is happening in terms of what instructions are fetched. Okay, so you're correct, but you're zoomed out a little. So if I were to take what you just said and zoom in, you get the right answer. So this is what you see. It is correct in the sense of, like what Ronit said, it's a strip. It's a strip that indicates that if you think about your address space, all of your addresses are kind of confined to a little strip. But if you actually zoom in on those addresses, it kind of looks like blah, 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 blah. And that's because like programs most of the time are in loops. So if your program is in a loop, then you're going to be like going through a few instructions and then like resetting and then going through those same few instructions and then resetting. You're doing this in time, so these strips kind of appear diagonal and you get multiple of them, and that's what you get, loop iterations. What about data memory accesses? So whenever you call a function or return from a function, you're moving like your program stack pointer around. Who knows what like a stack access pattern might look like? Yeah, someone was squiggling it out, and that's roughly the right answer. The only thing that's kind of strange is this flat region. So you push stuff onto the stack, you pop stuff off of the stack, and in most ISAs, you're going to be reading elements that are on the part of the stack that you just pushed, corresponding to like argument registers. And that's what this kind of no man's land, this straight horizontal strip is doing. And then finally, we have normal data accesses, so not associated with a data structure like the stack when you're pushing and popping, but there's still a lot of regularity in these access patterns. So you might have vector accesses or scalar accesses. And so if you kind of boil these different access patterns together, you get two properties bubbling to the top. And that is that program access patterns, by laws of nature in how we kind of construct programming languages and build large programs, these access patterns feature temporal and spatial locality. Everybody has heard these terms before in 61C? Awesome. So temporal locality, to recap, is when you touch the same memory location multiple times in quick succession. Spatial locality is when you touch nearby locations after touching a particular location. So going back to our original picture, the horizontal strips are temporal locality or evidence of it. And the kind of barcode rectangles are evidence of spatial locality. And that brings us to caches. Caches are how we try and exploit in a programmer transparent way temporal and spatial locality in levels of the memory hierarchy pyramid that are above DRAM and below the register file. So they're going to try to exploit both temporal and both spatial locality. At a very high level, a cache is an array built out of usually SRAM because it's closer to the CPU and therefore its capacity is smaller and we would like to be able to access it quickly. An array of data words that correspond to data that has been recently used, which means that it's going to be trying to exploit temporal locality, and coarsened into cache lines or cache blocks. So whenever we read a word from memory and it gets loaded into the cache, we're typically going to store nearby addresses associated with it as well and call all of these addresses together a cache line in the hopes that we're going to access those other addresses sometime in the future as well. Okay, cache algorithm. I think that everybody has seen this before, but just as a quick refresher, the cache is a content addressable memory. We send an address to it. The data corresponding to that address may be there or it may not be there. If it's there, it's called a hit, in which case you return the data. If it's not, it's a miss, and the cache has to perform some operation, usually seeking the data in a lower level of the memory hierarchy pyramid to go fetch the data. Caches have placement policies. Everybody has seen this picture from 61C, or is this picture no longer a thing? So caches have placement policies. They can be fully associative. They can be set associative. They can be direct mapped. I could never remember by looking at these like patterns what any of these terms meant. It was all very confusing when I was first taught it. So I prefer to think about a hardware cache in a different way. A hardware cache is simply a hardware optimized hash table. Everybody took 61B, knows what a hash table is? Okay. A hash table takes as input a key. It's going to store key value pairs. It's a content addressable memory. If you've ever used a dictionary or dict in Python, you've used what is probably a more abstract data structure, which is probably implemented as a hash table. So a hash table, an implementation of a content addressable memory or dictionary, takes a key as input. A hash function is going to take the key and output a hash, and that hash value is going to be used to choose one of several bins in the hash table. We're only going to visit one bin, the one corresponding to the hash. After we go to the bin corresponding to the hash, we're going to search the slots in the bin, each of which are key value pairs, and search for the key that matches our original input key. If it's there, we return the value there. That is equivalent to a cache hit. If it's not there, we have a cache miss. So a cache is just a hardware optimized hash table. The hash function of hardware caches, to be efficient in hardware, is super simple. A hash function might be very complicated, but a very simple hash function that tends to work pretty well is to just take a subset of the address bits, these are the so-called index bits, and use that to choose which bin or set we're going to go to. So in cache terminology, a hash table bin is a cache set. The slots in the bin are cache ways, and from that, we get all of our associativity flavors of cache. If you have a cache which has one bin and however many slots associated with that cache's capacity, you have a fully associative cache. If you have one slot and many bins, you have a direct mapped cache. If you have m slots and n bins, where both m and n are greater than 1, you have a set associative cache. To be optimal or more hardware friendly, we bound the number of slots per bin. If we had load imbalance where one bin could contain an infinitely large number of slots, and I were to stick you on a desert island and say, implement a hardware structure that implemented this, you'd be sad, because that is not easy to implement in hardware. You'd much rather just take a table like an SRAM array, which has a fixed capacity, and implement your cache out of that, which means that your bins are going to have a limited number of slots. For efficiency reasons, many caches, but not all, will read all the slots out in parallel. So in like a software data structures class, you may have talked about how the slots are implemented like as a linked list, where you kind of like traverse them sequentially. This is slow. To be as fast as possible, we're just going to read out all the slots in parallel. This may correspond to the design that you've seen in 61C. The key value pairs that are stored in each of the bins in each slot are sometimes stored separately. So you might store all the keys in one table and all the values in another table. This is an implementation choice that caches in hardware sometimes make, and this is what corresponds to a data and a tag array, but it's all the same thing. If you remember back from CS61C, you might remember that there's like several parts of an address. There's the cache line offset, there's the index bits, there's the tag, and you only check the upper bits of the tag to the keys in the key value pairs when you're actually traversing each bin. This is just a performance optimization or an area optimization because they realize that in a hash table, if you hash to a given bin, then some of the address bits of your key are guaranteed to match the keys that are stored in that bin for the hash functions that caches usually pick, namely just taking a subset of the address bits out as the set index bits and using that to choose your bin. So that is just an area optimization. Conceptually, what we're doing is key matching on the whole address, or that's a better way to think about it. Okay. Very quickly, we're going to do a whirlwind of one level down how we're actually going to implement these hardware optimized cache tables in hardware. So here is a direct mapped cache. Per what I said, we split the address into several fields: tag, index, block offset. Again, think hash table. Tag is a key, or it's a fraction of a key that we know we need to check based on our hash function, which is just take the k index bits and use that to select a set or a bin. And because this is a direct mapped cache, we have one slot per bin. The slot is here, the key is stored there, the value is stored there, and because we're storing a cache line as opposed to a single word. There are multiple elements there that we read out, and based on the block offset, we're going to, via a multiplexer and the select function, just like a column decoder, pick the actual word in the cache line that we need out. So this is a direct mapped cache. You could also organize things differently. Again, nothing's changed conceptually. This is just a hardware optimized hash table. But when we talk about the actual implementation, we can, just like with DRAM, swizzle the bits around that correspond to the address and instead use the low order bits for the tag and the index bits at the very top. Is this a good idea? Why is it not typically done like this? Anyone? So this is what we usually do, and this is what I'm now proposing we do. Is this a good idea or a bad idea? Yeah. You're absolutely right. What access pattern would this be awful for? Yeah, if you're striding through an array and your index bits are at the top of your address, you're striding through the array, your index bits are very seldom going to change because you're just like incrementing the address like a counter, which means you're going to repeatedly hit the same set and not actually use the cache. You're going to effectively use just one set in the cache. And because you only have one slot, you're using just 1 over, if you have S sets, 1 over S of the cache. Very bad. Two-way set associative alleviates this a little bit. So with a two-way set associative cache, again, think hardware optimized hash table. All we've done here is we've changed it so that instead of 1 slot per bin, we're going to allow 2 slots per bin. So what do? We do exactly what a hash table would do. So this is basically, you squint your eyes a little bit and you immediately see a hash table. You have the same hash function, index bits going into one of the bins, which corresponds to a row in these two tables. The two kind of red speckled cells are the 2 slots in that bin that we're going to read out. We're going to read them both out. We're going to check our tag as it comes out with the data, and we're going to do the same column decoder, quote unquote, style muxing to get the word that we want, along with checking whether there's a cache hit or miss, and we get our data out in exactly the same way. If you designed your cache and flipped the tag data, this design would do twice as good in the sense that 2 addresses would fit to the same set, but you still don't want to flip the order of those 2. And finally, we have set associative, which is just 1 bin, many slots. Per what we said, we're going to read all the slots out in parallel. That's exactly what we're doing here. We have our big tag, our big key, our block offset. We're going to read all the slots out. We're going to pick which word in each of the slots that we're actually going to read. So this mux is huge. This mux takes in all the bits of all the cache lines in the cache and picks not only the cache line that we're interested in, but also the word in that cache line that we're interested in. And we're going to do the exact same tag or key check on all of the elements that we've read out of the cache to determine whether it's a hit or a miss. If it's a hit, we grab our data. If it's a miss, we throw it away. Finally, or 2 more slides, 2 more minutes. Replacement policy. If we miss and our cache is full, we have to take one of the blocks already in the cache and replace it with another block. There are policies that try and choose for the set that we're accessing or the bin that we're accessing which block we should replace. This is not something that a hash table will need to do because a software hash table does not have a finite number of slots per bin. In a cache, we have to do it. The different policies, some of which you've probably heard before, are like first in, first out, which is just kind of rotating through the blocks that were filled. Least recently used, and you'll learn about an actual implementation of least recently used on Thursday, and random. This whole business with replacement policies is a bit second order for performance. Does anybody know why? When does a replacement policy matter? Yeah. Which corresponds to when you hit or miss in the cache. Yes. If you hit always in the cache, the replacement policy is irrelevant. If you miss in cache, the replacement policy comes into effect. You design your cache to minimize the miss rate and maximize the hit rate. So hopefully replacement policy is not too important. But for some workloads where the miss rate is high, it is important. So we have it. Last slide. Block size and spatial locality. We've already said this in slightly different ways, but when we access a word in the cache, we will typically not just bring that word in, but we will bring an entire block in. This is good for several reasons. The first reason is less tag overhead. So again, hardware optimized cache table, everything we're storing in the cache is a key value pair. If your value is very small relative to your key, then your key overhead is larger. So it'd be nice to have a very big block size and only have one key per block to minimize the tag overhead. So that's always nice. It also enables you to exploit spatial locality, in the hopes that when you access a particular offset in a line, you will soon access another offset in a line. If that happens, which occurs during like the stride access pattern that we just discussed, a larger block size will help. What are the disadvantages? Why not just set the block size to be infinitely large? Like, what's the limit here? Is that a dumb idea? Or is that a good idea? Yeah. Yeah, and that seems really bad. And the reason that's bad is that spatial locality only goes so far. So when you set your block line size, you want to be very careful to fetch an amount of data that will amortize the tag storage and be able to exploit available spatial locality, but without having a high risk of bringing data in that you won't access. If you access all of memory and your block line size is infinite, chances are you're not going to be accessing most of that memory shortly in the future. So all of that memory traffic will go to waste. So this is bad. Okay, and we're done. Sorry for kind of speeding up. I wanted to get to memory 2 by the end so that our famous GSIs could pick up where I left off coming Thursday. Remember, I am out. Office hours for all the GSIs is on, but I will be out tomorrow, so no office hours. I will see everybody next Tuesday.